Hi friends, in this video we are going to discuss about the design of one-way slab. So we are going to discuss about the introduction of the one-way slab and how we can design it practically. So before going ahead, please make sure to subscribe our channel for future videos. So let's get started. From its definition, a slab is one-way slab when slab is supported on two edges and it bends in only one direction. So as you can see in this picture, the load has applied over its surface and the slab is bending only in one direction, which is its shorter side. If we see it another example, in this example, as you can see, the beam is supported in four direction, but sometimes it is very difficult to understand that which kind of slab it is, whether it is a one-way slab or it is two-way slab. So in order to judge it very well, we go for some other criterias to analyze it whether it is a one-way or a two-way slab. So even when a rectangular slab is supported on all the four edges, the slab may be considered as one-way slab if the length to breadth of the slab is equal to or greater than 2. Let's take another example. If you can see, the span here of a slab is 10 meter and its length is 20 meter. So we have to decide whether it is one-way slab or a two-way slab. So of course it's very easy. We have to divide it. Length by width, 20 by 10 is equal to 2. So here, if the length to breadth ratio of slab is equal or greater than 2, then it is called one-way slab. So this is a very simple formula they can use in order to differentiate between the one-way and two-way slabs. Also, one-way slab is designed for spanning direction alone. The main tension reinforcement bars of such slabs run parallel to span. For the transverse direction, the minimum amount of shrinkage reinforcement is provided. So here the question is which span is the shorter direction and where the main tension reinforcing bars are provided. So as you can look in the figure, the span 10 meter is the shorter direction. So we have to provide man bars in this shorter direction, having the required spacing from one end to another end. So this and similarly, the transverse bars or the bars perpendicular to the shorter direction is also provided. That are also called shrinkage reinforcement. So let's jump to an example, which is the design of one-way slab. So here the data is given. Concrete strength is equal to 4 ksi, steel grade is equal to 60 ksi, live load is equal to 220 psf, and dead load is equal to slab self weight. So the span of slab is 10 feet. So by using the given data, we are actually going to design a slab. So same example is here and same data is used to design this slab. So if we see it in a 3D view, here is 10 feet is the span of this slab, which is the shorter direction where actually the load is distributed. So we have to design it for a small strip, which is 1 feet, right? So we have considered a small strip of this slab, which is also 12 inches, and its depth is also supposed. So the given data is already given. FC is equal to 4 ksi, Fy is equal to 60 ksi, and live load is equal to 220 psf. So the dead load is actually same of self load or self weight. So we have to design it. Let's assume that the d, which is the depth from the center of the steel to the upper surface of the slab, is equal to h minus 1. H is the total height of the slab, which is to be assumed. So d, small d, is also called critical depth. If we take an example, here h is the total depth of this slab, and for a specific cross section which is 12 inches, we have to provide a clear cover of 3 or 4 inches. And D here is the critical depth from center of the steel to the top of the slab. And center of steel is actually the main steel, where the depth or critical depth is to be calculated. So let's go ahead and design the various parameters of this slab. So for that things we have to assume the minimum height of the slab. For that we have a table from a well-known book, which is it's chapter number 13. So for simply supported, we can use L over 20. And for one and continuous, we can take also L over 24. So in our case, our slab is simply supported. I mean, it has only one span and it is to be designed for one span. So its depth to be assumed will be L by 20. So L is 10 over 20, which is 0.5, but we have to calculate it in inches. So the depth is 6 inches. It means that we have to provide 6-inch slab, which is minimum depth of this slab. So in order to calculate the critical depth, we have to subtract the total height from its clear cover, or you can say from the height of the center of the main bar to its lower bottom depth. So we have to calculate the density. So to calculate density, we have to multiply the volume of this cross section of this slab with its density. So we have to put values of the density of the concrete and also its cross section. So here density of the concrete really depends on the mixed ratio, that what mixed ratio have been used to make the slab. So we are using the normal concrete here, a normal strength concrete. So its density will be 150 pound per CFT multiplied by BH. B is the unit strip width and H is the height of this strip. So by putting these values of width and height of this strip of the slab, we can get the answer, which is equal to 0.15 into B, which is 12 inches or 1 feet, or multiply by 0.5 feet. So we have to calculate the dead load in kip per feet. Here you can ask the question that how we converted 150 into 0.5. So the load, which was 150 pound per CFD, is converted into 0.5 kip per feet, or 0.15 kip per feet by dividing with 1000. So for live load, which is already given 220 PSF, is similarly converted into live load by converting it into kip by dividing it with 1000. So we have 0.22 kip per feet square, and to convert it into simple kip per feet, we have to just multiply it with 1 feet. So the live load will be 0.22 kip per feet. So here we have calculated almost its live load and dead load. Now it is very easy to go ahead and make some further calculations. So the design load formula will be 1.2 dead load plus 1.6 live load. So here in this formula we have to put these values. The dead load will be 0.075 and the live load will be 0.22. So multiplying these factors, we have calculated the uniformly distributed load, which is 0.442 kip per feet. Similarly, we have to calculate the movement due to these dead loads and live loads. So for that, we have a very simple formula depending upon the end conditions. So it varies, depends on the supports conditions. So which is WUL square by 8. So WU is 0.442 and length is 10. So dividing it with 8, we have got 5.5 kip feet. Right, so this is the moment which is produced by these dead loads and live loads on this slab strip of 1 feet. So to convert it into inches, simply multiply it with 12. The answer is 66.30 cubic inches. Now we have to calculate the rho, which is the steel ratio. This is a quite long formula, which is 0.85 Fc dash or Fy into 1 minus square root of 1 minus mu by 0.85 phi Fc dash Bd square. This is a long formula which is also can be found from the book. So by putting all these values or rearranging it, we can also got Bd square. So this is the rearrangement of the above formula. We can also rearrange it. So if you want to watch this, you can watch our previous lecture to better understand it. So by putting the values 0.85 into Fc dash, which was 4 ksi, divided by Fy, which was 60, into 1 minus square root 1 minus 2 into mu, that was the moment, which was already calculated 66.30, divided by 0.85 into 5, which is to be assumed as 0.9. So by this is an assumption that we can make. So 0.9 multiplied by Fc dash, again 4, multiplied by 12. So 12 is actually unit width of the strip, which is to be considered for designing of this slab. So this is actually similar to design of one-way slab or beam. So rho has calculated here, which is 0.00425, which is to be used to calculate the area of steel. So the required area of steel can be calculated by using this formula, rho required BD. So rho is 0.00425 into 12 into 5. So the answer is 0.22255 inch square. So similarly, we have to calculate the temperature steel. Temperature steel, we have to go for some ACI or some course, which is also present in the book. So we are using the grade 40 concrete. So for grade 40 steel, so for that steel, we have to use the ratio or steel ratio, which is to be in our case 0.0020. So we can easily select which kind of ratio we can use. So in our case, we are using 60 grade steel. So for 60 grade steel, our second option will be 0.0018 will be better. So by using this formula for temperature steels is equal to 0.0018 BH. So the temperature steel is equal to, by putting all these values, we have got the value, which is 0.1296 inch square. So now we have calculated the temperature steel and also main steel. Now go to the design solution for the reinforcement pattern and the number of bars. So for the main steel, we have to calculate the spacing of the steel between the man bars. So for that, we have the formula which is minimum of 3h or 18 inches. So h is the height of the slab. In both cases, 3h will be 18 inches or both 18 inches. So minimum which is to be selected is 18 inches. So the temperature steel will be also minimum for 5h or 18 inches. So similarly, by putting these values, 5 into 6 6 fives are 30 into 18 inches. So here the minimum spacing, maximum spacing which is to be provided is 18. So we have to provide reinforcement less than 18 inches. So now the question in our case is which kind of reinforcement spacing we have to select. So this is a very critical question. So for that, we have to consider some kind of options and look at the tables. So for main reinforcement, we have to go for a table. In this table, as we already calculated the area of the man bar steel, which was in previous, we have already calculated. So we have to check the area of these steel bars, and we have to locate the spacing against the area. So first we are considering number 3 bars. If we see it, then we can get 0.26 inch square. So for 0.2 inch square, 26 inch square, our spacing is 5 inches. So this is the required spacing for main steel. So if we go for 4 number 4 bars, then we can also select 0.26 inch square versus number 9 bar. 0.26 inch square. For that area we can use number 4 bar and provide spacing 9. So now the question is which is to be used. So we can use number 4 bar at the rate of 9 inches because it is good to provide greater spacing. And now for the temperature reinforcement, we had the area 0.1296 inch square. Similarly, we have to locate this area in this table, that which area is that which number of bar or spacing to be provided for. So if we look for the number 3 bars, then we have the spacing of 10 inches. So obviously we can take it, this is a perfect combination. So for temperature steels, number 3 bars at the rate of 10 inch center to center will be the or required temperature steel bars. So if we just take it cross section and finalize our design, here 3 or 4 is the clear spacing, clear cover of the bars. This is the man bar, which is number 4 at the rate of 9 inches center to center. And in case of temperature bars, we have these bars which we have already calculated, which was number 3 at the rate of 10 inches center to center. So this was our final design that we have calculated by using various formulas. So I hope that you have learned now. Now you have to go ahead and design your example for better understanding. So for more videos, please subscribe to our channel, Civil Engineering World.